In this video, we're going to talk a little bit about hypothesis testing. So let's start off with an example. I'll let you guys read this example for a moment. Okay, so to think about this question, we already have one approach that will work and give us an answer, and that is to build a confidence interval. So if you're taking that approach, what you would do is calculate a confidence interval, which is p hat plus or minus the margin of error. And given this confidence interval, you would then compare this hypothesized 28% to that confidence interval. And if it turns out, for example, that 28% lies inside of the confidence interval, that would suggest that the data indicates the severity of the problem is not different for African Americans. Because again, the confidence interval gives us a range of values for the true P that are consistent with the data that we've observed. On the flip side, if 28% did not lie in the confidence interval, that would suggest that 0.28 is inconsistent with the data that we've collected, and therefore that the severity of the problem seems to be different for African Americans. So let's go right ahead and compute this confidence interval so we get a sense of what that answer looks like. So of course I'll need a confidence level for us to be able to proceed with the calculation. Just for convenience, I'm going to use a 95% confidence level. So based on that, you guys know that Z star is going to be 1.96. And we can get that by using the Q norm of 0.975. So we're going to do 0.32 plus or minus the margin of error. Crunching the numbers, we see that this confidence interval evaluates to 0.288 to 0.352. So this is a case where 0.28 is not inside of our confidence interval, and therefore we would say that the data indicates the severity of the problem is different for African Americans. In fact, you can go as far to say that this is a more severe problem for African Americans because 0.28 is entirely below our confidence interval. So now let's think of a more direct way of tackling this problem. So a more direct approach would involve the specification of a proposed hypothetical population parameter, so giving a proposal for P, and then checking to see if the data actually support that value of P. So how we do this is we actually consider a formal setup where we have two hypotheses. So we've got something called a null hypothesis and something called an alternative hypothesis. Okay, so in this case, the null hypothesis represents the default frame of mind. So in relation to example 1, P is 0.28. And the alternative hypothesis, it is the claim we are trying to show by collecting evidence from our observations. So in this case, we are looking to see whether or not P is not equal to 0.28 for African Americans. So just to be really specific here, we have P, which is the population proportion, and then we have P0, or P0, which is the hypothesized value for the population proportion under the null hypothesis. So we're really considering these two different hypotheses and thinking about which of them might be a better representation of the sample that we've collected. And we've got two options here. So our first option is that we can reject the null hypothesis in favor of the alternative hypothesis. Option 2 says that we don't have enough evidence to reject the null hypothesis. So our null hypothesis is quite consistent with what we've observed. So given these two options, we now have to figure out exactly which one of them we are going to take. And to do this, we go out and we collect our evidence, and our evidence is entirely encapsulated in this p hat value. Of course, also n, our sample size, because those really go hand in hand into our calculations. So how do we actually proceed here? Well, we're going to actually start by assuming that the null hypothesis is true. This is the whole idea of hypothesis testing. We start by assuming the null hypothesis is true, very much like a jury will assume that an alleged criminal is actually innocent, and we then have to collect data to disprove that assumption. We already know the behavior of p hat based on the central limit theorem, if only we can nail down a true population proportion to consider. So in this case we do, because when we assume the null hypothesis to be true, we simply assume that P is equal to P naught. So under the central limit theorem, we determine that P hat follows this specific normal distribution, which is the same thing that you've seen before when we first talked about sampling distributions, except now we are plugging in P naught for P. Because remember, our assumption is that the null hypothesis is true. Okay, so now that we have this in mind, it's straightforward for us to compute a z-score corresponding to an observed p hat. All we have to do is go to our trusty z-score formula, which is to take the sample statistic, subtract away our hypothesized mean, and then divide by the hypothesized standard deviation. So I'm using a little bit of a funky notation here to be consistent with the book. Q naught is simply equal to 1 minus P naught, okay, just to be clear here. So a very extreme z suggests that our data are fairly inconsistent with the null hypothesis, and then we are more likely to take option 1 in that case. Otherwise, if z is small in magnitude, we find that the data might be described by the null hypothesis, so we'll probably stick with option 2. So I hope this builds the intuition behind how hypothesis testing works. So next we can loop back into our question regarding example 1. What is the value of z in that case? So to do this calculation, I'm just going to use the formula. So if we know anything about the 68, 95, 99.7 rule, we would say that this value of z is very, very unusual. Right? We expect to see less than 5% of the data beyond z-scores of plus or minus 2. So in this case, z does appear to be extreme, and we are tempted to go for option 1. So we'd like to be able to be a bit more precise about this and not just talk about how extreme z is in a vague sense, but also be able to quantify just how extreme is extreme and define a decision boundary for deciding to reject or to not reject the null hypothesis. So first we have a p-value, which represents the probability that gets associated with the z-score we just computed under the assumption that the null hypothesis is true. So the way I have written it here, it is the probability of obtaining results as extreme or more extreme than our observed p-hat, assuming the null hypothesis to be true. And you can see that with the current setup with a two-sided alternative, meaning that the operator here is a not equal sign, we calculate our p-value to be the probability of observing a z-score that is either too small in the negative direction or too large in the positive direction. Okay, so you can actually calculate this using z, a standard normal random variable. And so all this does is translate the z-score to an actual probability. You can see where we're going with this, right? So if that probability ends up being below some threshold, we're going to reject the null hypothesis because it would suggest that the chance of observing something as extreme as what we did under the assumption that the null hypothesis is true is just really, really small. Put another way, if you get a p-value that is too small, it would suggest that the null hypothesis do not seem to describe where our data is coming from. So then the question becomes, where do we set that cutoff? It turns out that there is no one of a cutoff to use. So what we have is something called the significance level, which we use as alpha, and this is the exact threshold we would like to use for our p-value. And it represents our tolerance for making a mistake in our decision to reject the null hypothesis. So now let's just go back to example 1 again, and we are now given a specific alpha level, and we also have an actual z-score to consider. So let's just go ahead and wrap up our calculations. So if you guys recall, z was 2.52. To draw this for you guys, we would see a normal distribution here. So here we have a really poorly drawn normal distribution that's tempting to illustrate what we're actually doing here in calculating the p-value. We have an actual normal density curve here, standard normal density curve, and all we're trying to do is calculate the area beyond the tails, because the area beyond the tails represent values that are more extreme than the value of p hat that we've obtained from the sample. So here is our p-value calculation. So notice that despite my poorly drawn picture, the normal distribution is actually meant to be symmetric, meaning that the area in this lower tail should actually be the same as the area in this upper tail. And so all we need to do is figure out the probability in one of these tails and then double it. So that's exactly what I'm going to do. For convenience, since R allows me the flexibility of calculating lower tail probabilities, I'm going to calculate the left tail. That's a little bit easier here, right? So just plugging this into my p-norm, I get a p-value of 0.012, and now we just have to compare the p-value to our alpha of 0.05, and because the p-value here is less than 0.05, we would reject the null hypothesis and conclude that at a significance level of 0.05, we find the problem of inadequate healthcare is different for African Americans. So I hope you guys see that regardless of whether you take the confidence interval approach or the hypothesis testing approach, you actually will arrive at the same conclusion.